Infrared thermography, also sometimes known generally as radiation thermometry, is a non-contact temperature measurement technique that makes use of the correlating relationship between the amount of infrared radiation that is emitted by objects and that object's temperature. The general physical operating principle of these devices is to convert radiated energy into heat and then into an electrical signal proportional to the amount of infrared radiation. Infrared radiation detectors generally fall into two categories: passive infrared detectors that absorb incoming radiation only, and active far-infrared detectors that also emit infrared radiation. Both rely on a detector system that is used to absorb the radiation to heat the detection element, and then use the subsequent temperature rise to trigger a corresponding change in a physical mechanism that can then be measured. One such example is a resistive bolometer array, which runs a wire through a material that experiences a change in resistance when exposed to a change in temperature, then measuring that change in resistance. Another thermal detector is the bimetallic cantilever array, which is based on fine metallic strips that bend as its temperature changes. The degree of bending is then measured by measuring the capacitance between the bimetallic strip and a fixed capacitor electrode. An alternative method of detection is a photon or quantum detector. This method relies on the interaction of photons with charge carriers such as electrons to directly alter their energy state. Essentially, they are photodetectors whose semiconductor material is doped to achieve high sensitivity to infrared radiation as opposed to visible light. The main physical phenomenon by which infrared thermography operates is the emission of electromagnetic radiation. All temperatures above absolute zero will cause matter to emit electromagnetic radiation, and the amount and distribution over the wavelength spectrum correlates directly to the temperature of an object. Since the maximum amplitude of the energy transmitted at a given frequency is given by its temperature and surface emissivity, it is only possible to know the gradient of the surface temperature for an object without the surface emissivity value of that object. Thus, to obtain temperature values, infrared thermographs require the use of black body objects, materials with constant emissivity values for a range of spectrums, for calibration. Since the emissivity values are known and constant, it is possible to use the corresponding curve to calibrate for temperature and measure other objects without knowing their precise emissivity values, and finding their temperature relative to that of the black body object.
Despite its wide range of applications, there are a few notable limitations of infrared thermography. From the broadest standpoint, infrared cameras can help detect abnormalities in the thermal distribution of an object, but they cannot directly identify the cause of this abnormality. In many cases, determining the cause of a potential issue detected using infrared thermography involves the use of either intuition or pairing this technology with another technique, such as vibration analysis, oil analysis, or ultrasonic inspections. In general, the most popular infrared cameras are designed to perform well for a wide range of applications. Although each model is slightly different, the general temperature range for a high-end thermal camera is from -4 degrees Celsius to 650 degrees Celsius, with the best cameras being able to measure up to 1200 degrees Celsius. In terms of sensitivity, the best infrared cameras can detect temperature changes as small as 0.05 degrees Celsius, which is more than adequate for most applications.
The two main sources of error for an infrared thermograph include the loss of energy as infrared radiation passes through the atmosphere and the infrared radiation that is reflected off of the screen or detector of the thermograph. Regardless of the radiation absorption method, some of the radiation will be reflected, resulting in less radiation absorbed, a weaker electrical signal response, and a lower reading. One way to mitigate this error is to install a reflective pane on the inside of the device that allows the radiation to travel into the sensor, then reflects any outgoing radiation back to compensate. The other source of error is energy dissipated in the atmosphere. This source of error is much more difficult to remove unless the thermograph is used in a vacuum.
There are many factors that limit the performance of infrared cameras, the most significant of which are the emissivity of the targeted object, the reflected ambient temperature, and the atmospheric temperature. These factors are a few sources which may cause error in the output of the device. In general, they contribute to a plus or minus 2 degrees Celsius uncertainty associated with most infrared cameras. This is actually quite high compared to their advertised sensitivity. The non-contact nature of infrared thermography allows it to have a diverse range of applications. It is a measurement technique that is frequently used in all domains of science, including medical and biological research. In engineering, however, it is most commonly used in the inspection of different systems. The ability to detect thermal abnormalities can help identify defects, inefficiencies, and potential points of failure of a given system. The fact that it can take thermal measurements from a distance is valuable because it increases the safety and practicality of measuring temperature. It also allows maintenance inspections to be conducted while the system continues to operate at normal conditions. This adds to both the economic and time-based efficiency of this measurement technique. Infrared thermography is becoming increasingly popular in building inspection, as it allows users to conduct maintenance checks while reducing the risks of falls and other associated injuries. For example, the picture here shows how an infrared camera is being used to detect a roof leak without the need to physically access the roof. The temperature distribution over the surface of the ceiling has a clear abnormality in the blue region, which indicates a lower temperature. This is an indication that there is a water leakage resulting from a fault in the construction of the roof. In electrical engineering, there is a strong correlation between the overheating of a component and its eventual failure. As a result, infrared thermography can be used to detect overheating of certain electrical components to prevent circuit failure. In this specific example, we see that in the thermal image produced by the infrared camera, one wire has a significantly brighter color than the others. This indicates that there is a wiring connection issue somewhere in the circuit that is causing overheating and that can potentially lead to system failure if not properly addressed. From a mechanical engineering standpoint, infrared thermography is commonly used in the inspection of various mechanical components. It can help perform maintenance on everything from an entire motor all the way down to a single bearing. Again, infrared cameras use the concept of abnormal thermal distribution to help identify faults within the expected functioning of a system. In mechanical systems, overheating can be caused as a result of unwanted friction, component misalignment, or poor circulation of cooling air or liquids. In this specific example, the motor is overheating, as indicated by the red region of the thermal image. Although they are not clearly exposed, the bearings of the motor are often a source of overheating due to poor lubrication, general wear, or even the fact that it is simply a poor bearing choice. Regardless of the specific cause of the bearing malfunction, infrared thermography can be used to detect a potential source of failure of this motor and indicate that further maintenance is required in order to prevent severe consequences. These are just a few examples of the many engineering-specific applications of infrared thermography. As we can see, its simple working principle paired with its use of the electromagnetic spectrum, which is a very well-studied and well-understood domain of physics, are two factors which make infrared thermography a very appealing optical measurement technique. As a result, we can fully expect infrared thermography to remain a valuable tool for many engineering applications in years to come.